Hello and welcome to this video where we're going to be taking a look at one square matrix that I'd like to think ties the knot between the complex world and the matrix world. So let's get right into it. Okay, to start with, I'm going to be defining the Maclaurin series of e to the some power, let's say e to the power of a. And note that the Maclaurin series is basically the Taylor series centered at 0. Okay, so e to the power of some a is equal to the summation of 1 over r factorial times a to the power of r from r is 0 to infinity. Okay, so now I'm going to be telling you guys what the matrix actually is. So I'm going to call this matrix M, and it's equal to 0, minus 1, 1, 0. And this is the special matrix that we're going to be talking about in this video. So before we start doing all kinds of fancy stuff with this matrix, I want to show you guys the pattern in m to the power of r for different values of r. And I'm going to define m to the power of 0 to be the identity matrix, which is basically 1, 0, 0, 1. Okay, so m to the power of 1 is obviously just m itself, so it's just going to be 0, minus 1, 1, 0. M squared, we just need to multiply m out, m by itself, so we're going to be getting minus 1, 0, 0, minus 1. And notice that this is just minus I. Okay, we can just factor out a minus 1 out, and we're left with the identity matrix. M cubed, m cubed is basically m squared times m, and minus I times m is just going to give us minus m. And if we multiply that by m to the power of 4, we're just going to get I again, because m squared is minus I, and minus of minus I is just I. So it repeats every 4 terms. Okay, so what I'm about to do next may feel a bit weird for some of you guys, because you may not be used to it. So what I'm going to be doing is taking a number to the power of a matrix. Now this is not really well defined, and that's why I've written out the Maclaurin series of e to the a, because it's easy to take a matrix to some power, but it's hard to take a number to the power of the matrix. Okay, so now we're going to be taking e to the power of that matrix to see what happens. Okay, so now I'm going to take e to the power of m, and not just m, but m times some value theta, and you'll see why I'm doing this later on. So this is equal to the summation from r is 0 to infinity of 1 divided by r factorial times m to the r times theta to the r. Okay, so that's going to give us, when r is 0, we're just going to get m to the power of 0. When r is 1, we're going to get m theta. When r is 2, we're going to get 1 over 2 factorial m squared theta squared. When r is 3, we're going to get 1 over 3 factorial m cubed theta cubed, and so on and so on. So now I'm going to substitute the values for m squared, m cubed, and all that into here. So m to the power of 0 is just I. M to the power of 1 is just m. We don't need to substitute anything for that. M squared is minus I, so we're going to get 1 over 2 factorial times minus I times theta squared. And then m cubed is minus m, so we're going to get 1 over 3 factorial. 1 over 3 factorial times minus m times theta cubed, and so on and so on. So what I'm going to do now is I'm going to factor out the I out of every even term. So I'm going to factor out I from here, and from every other even term. So if I factor out the I, we get 1 minus 1 over 2 factorial theta squared, and then we're going to get 1 over 4 factorial theta to the 4 minus plus, and so on, with every even term. And now I'm going to factor out m out of every odd term. So out of here, here, and all other odd terms. So if I factor out the m, we're going to get theta minus a third theta cubed plus a fifth theta to the 5 minus plus, and so on. And now some of you may or may not already know that these two expansions here are actually the Maclaurin series of sine and cosine. So this one is cosine theta, and this one here is sine theta. Now I'm going to leave it as a task for you guys to derive that yourselves and convince yourselves of that. But moving on, we've just shown that e to the m theta equals I cosine theta plus m sine theta. Okay, so I'm just going to clear up the board and I'll meet you then. Okay, so far we figured out that e to the m theta is equal to this expression here, where m is this matrix here and I is this I is the identity matrix here, and theta is just some arbitrary number. Okay, so let's substitute in m and I. So e to the m theta equals 1001 times cosine theta plus 0 minus 1 10 times sine theta. Now it's totally fine to consider cosine theta and sine theta as a scalar and multiply it into the matrix. So it's going to become cosine theta 0 0 cosine theta plus 0 minus sine theta 0. Okay, so now we're just going to add it up. We get cosine theta minus sine theta, and cosine theta. And voila! You may or may not already know that this is actually a rotation matrix. This matrix rotates a point about the origin anticlockwise by theta radians. And now it's really important that theta is in radians because we've used the Maclaurin and the Maclaurin series for sine and cosine, which involves knowing the derivatives of sine and cosine, which are only defined for radians. Okay, so now some bells should be ringing in your heads, because there is another function that rotates points about the origin by some angle anticlockwise, and that is our beloved e to the I theta. If we multiply a complex number z by e to the I theta, it rotates that complex number theta radians anticlockwise about the origin. Now that begs the question, does e to the I theta equal e to the m theta? And does that mean I equals m? So I equals a matrix. Saying that makes me feel weird, but I think there's a really fascinating relationship there. And really strictly speaking, they are not actually equal to each other, and it's a very debatable thing to say, because some things are defined for I that are not defined for that matrix. For example, you can divide by I, you can divide any number by I in fact, but you can't divide by a matrix. You can only find inverse of a matrix, which is kind of like the division, but not really. But everything I can do, except division, the matrix M can do. And I like to think of this matrix M as like a subset of the properties of I, but in the matrix world. So whatever I does in the complex world, M does in the matrix world. And I feel like there is something more fundamental to this. If more research is done into this, and I myself am investigating this property, to try finding any deeper connections. I feel like we can understand something deeper or something more fundamental about the nature of the number I. But I thought this was a really cool relationship here, so I wanted to show it to you guys. But yeah, as always, thank you very much for watching this video, and I hope to see you in my next video. Bye!